Hello students, welcome to EC Engineering. In this video, we are going to see the evaluation of generalized error coefficients. So before dealing with the evaluation of generalized error coefficient, you should aware of an generalized error coefficients what it is, so that you refer our previous video. So after completing the previous video, you come back to the evaluation of the same. The description box gives you the previous video link. So in this evaluation of generalized error coefficient, the error coefficient is given as, from the previous video you can definitely aware of the expression C of n equal to minus 1 per n integral 0 to t capital T per n. This capital T denotes dummy variable, dummy f of t dt. And I want to again refresh you the error coefficient in S domain takes up the value E of s equal to f of s r of s, or E of s equal to 1 by 1 plus g of s h of s into r of s, where f of s equal to 1 by 1 plus g of s h of s. With this small refreshment of an previous topic, we get into the today's topic. Students, listen carefully the procedure, how it developed. Then only you could clearly understand the concepts behind the things, so that we are well aware of generalized error coefficient Cn expression and f of s expression. Now we know that in order to convert from time domain variable into frequency domain, we need to make an Laplace transform. So hence, by the definition of a Laplace transform, f of s is equal to integral 0 to t f of t e power minus st into dt. Now freeze this expression as expression number 2.67. On taking an limits s tends to 0 on both the sides of this expression, then it will becomes expression like this. Simply put limits s tends to 0 on both the sides. Now our expression becomes limit s tends to 0. So take into the s term. So all other terms here leave it. See, t integral 0 to t f of t terms, then limits tends to 0 comes inside, where limits s tends to 0, then this term becomes 1. So we get only f of t into dt. This f of t into dt integral part is considered as c0. So left side we have limits s tends to 0 f of s. Now we can write c of s is c of 0 equal to, here c of not equal to limit s tends to 0 f of s. You freeze this expression as 2.68 second unit. Now in the next step, differentiate with respect to s, the previous expression. So here it becomes d by ds of f of s equal to d by ds of limit integral 0 to t f of t e power minus st into dt. take d by ds inside, it becomes, differentiating the terms, it becomes minus t e power minus st. Means take minus here outside an integral part, it becomes t into f of t e power minus st into dt. Now freeze this expression as 2.69. Now again put limits s tends to 0. So here put it over limit s tends to 0, it will becomes limit s tends to 0 d by ds of f of s. Again limit s tends to 0, this term becomes like this. Then take s tends to 0 inside nearer to the e power minus st. Again this term becomes 1. So we get only minus of integral 0 to t f of t dt. Now we consider it as C1. So what is C1? C1 equal to this part. Is it so? So we can write C1 equal to limits s tends to 0 d by ds of f of s, and freeze it as some expression 2.70. Now take a next step. Both the sides differentiate with respect to s. So here d by ds of again d by ds of f of s equal to, what is the value here? C1 value. C1 value is already known one. Put it over C1 value. So here this term becomes d square by ds square f of s. Here we are going to differentiate the term. So d by ds of e power st. How it comes? It comes as minus t e power minus st. Here one minus t, here one more minus t. So it becomes plus t square, then all the terms are comes as it is. Now freeze this as expression number 2.71. Again coming back by considering the same expression. Now apply s tends to 0 on both the sides. Again do the same thing. Integral limits s tends to 0, it becomes 1. So the value is t square f of t dt. Now consider this as a C2. So C2 equal to this one. C2 equal to limit s tends to 0 d by dt of f of s. So what we can infer from this expression C0, C1, C2, all the expression shows that limit s tends to 0, if it is C2, it is d square by ds square. So we can make an generalized formula Cn equal to limit s tends to 0 d power n by ds power n f of s. So as far as now we have completed how to evaluate generalized error coefficients of C0, generalized error coefficient of C1, C2 and the general expression. Now the next small subdivision, what should be the correlation between static and dynamic error coefficient? Static means stable, means it does not depends on time. Dynamic changes with respect to time. Now we are going to correlate both static and dynamic error coefficients for ease of our convenience. The various dynamic error coefficients can be used to find the static error coefficients. What are static error coefficients? Kp, Kv, Ka. So from this following expressions we can relate both. How to relate both? See, consider C naught. We are all well aware of C naught expression just before we discussed. Limit s tends to 0 f of s. What is f of s? 1 by 1 plus g of s h of s. Limit s tends to 0. So put it over only the s terms. What is this s term? This s term is means limit s tends to 0. G of s h of s is none other than kp. So we can write C naught equal to 1 by 1 plus kp. Similarly, it's applicable for C1 equal to 1 by kv, C2 equal to 1 by ka. So students, you just aware of the things. Go through the video once again. You can clearly understand the concepts behind, which is most relevantly useful for doing an part B aspect of an question solution part. Students, thanks for your cooperation, and do watch the video again and again to practice yourself and share the things to your friends also. Thank you, students.